I'm going to give you three modes of natural selection. You can expect these graphs on the exam, or you can expect, maybe a word problem. I'm going to give you an example of that as well. So three types are directional, disruptive, and stabilizing. This one is the easiest to understand, directional. So we're going to use the same peppered moth example for the directional selection. In directional selection, one phenotype in this example, the color is favored over another. This is a histogram, and here is showing increasing pigmentation, color, number of individuals, and this is the original population. This is how it is. And then the habitat changed. So let's say the Industrial Revolution happened, the habitat changed, and now the trees turn more dark colored. And over time, this is going to shift towards dark because these ones are easily detectable. They get eaten more often, they reproduce less, and then the Leo frequencies for this increases. So the population is going to shift towards dark color because that's the phenotype that's favored over this one. So that's directional selection. Any questions on directional selection? No? And then we have disruptive selection. So disruptive selection, in this, extreme phenotypes are favored over intermediate. Intermediate, this word was on the exam. Few of you guys asked me what it meant. It meant in between. So it's in between, medium phenotype. So there is a light color snail, there is dark color snail. Maybe they're living in an environment where there are light color rocks and then dark color rocks, but there's no medium color rocks. So this is the original population. So I'm just gonna say there are no medium color rocks. There's only light or dark color rocks. So these ones get detected more easily and they get maybe eaten up. And the habitat changes. So this was the original where there were all types of rocks, and then the habitat changed. Now you only have dark color rocks and light color rocks. So the disruptor selection, this population or this allele in the population goes down because it's not favored by natural selection. So you have more of light and dark. So extreme phenotypes are favored, but this one is not favored. So that's disruptive selection. Then we have stabilizing selection. I have example of humans for this. So in this one, intermediate phenotype is favored over the extreme phenotypes. So here is showing birth weight, number of individuals. I'm going to say the head size for human babies. If you have a smaller head size, that's not favored. If you have a large head size, that's not favored. If you have just right head size, that's favored. So that's stabilizing selection. So this is the original population. Over time, it kind of shifts towards the middle. So I don't know if you guys heard about microcephaly. So if you have a smaller head, then you're probably not going to live very long. Maybe there are some other issues that arise. Same with the larger head size. It's going to be hard for the big head size to pass through the birth canal. We didn't have, the modern medicine or procedures, maybe mom and baby both die. So in old times, because the head cannot pass through the birth canal. So just medium head size is the one that's favored here, so the middle one. Any questions on stabilizing or disruptive or directional selection? No? Okay. So there's a question for you guys. In very sunny places such as Africa and India, exposures to UV radiation selects for darker skin color. What type of natural selection is this?
Directional.
Directional. So this is, you can compare this example to the peppered moth example. We were also comparing two colors there. So that is directional selection. Okay. So now we're going to talk about other stuff that can also cause evolution. So if you guys remember, I said natural selection is not required for evolution to happen. So evolution can happen other ways as well. So just natural selection is just one of the things on this list. Another one is mutation, genetic drift, non-random mating, and migration. So immigration or emigration. Immigration with the I, emigration with the E. So people coming in or people leaving. Let's talk about these. So you already know what natural selection is. You know what mutation is. We talked about this before. So let's talk about genetic drift. So genetic drift happens by chance. So it's most common in small populations. So here's an example. So this is a jar filled with these blue and orange balls. Now, since it's random, by random chance, the blue, here's only one blue ball that got picked, whereas most of them are orange. So the frequency is 9 to 1 here. And then you restock these with that frequency. Now, there's a higher chance that these orange balls are gonna get picked because they're higher in number. So now this is your frequency. And then this is your next generation for that. So just by random chance, some of the alleles in population can go extinct just because they didn't get picked, and because they didn't get picked for the next generation, now there's a higher chance, even a higher chance the other allele is going to get picked because it's higher in number. So by random chance through genetic drift, some alleles can go extinct, especially if it's a small population. Then there's something that's called founder's effect. So I'm gonna use an example, use the example of pilgrims. So pilgrims in Europe, um, they didn't like some of the things that were happening in Europe. So they moved to North America. They were a small population. So let's see, this is the population in Europe. All these different colors are different alleles. And these are the pilgrims. It's a blue, red, and yellow. So they come to North America, but they only mate with within their population. So they do not mate with the population that's, you know, outside. So they are mating with maybe, you know, their cousins or whatever. So the only alleles that they have are these blue, red, and yellow, because they are only sticking within that population. Now, if they were to go back to Europe, there are all these different alleles available. There's a genetic diversity in the original population. But if a colony out of this original population goes out, it's isolated, then the allele frequencies that in that colony change, and the only ones that are available are these three here. So when only a few individuals establish a new population, the allele frequencies change, and that's called founder effect. So, you know, if they have an extra finger here, that might, you know, end up getting a whole population, because also increases the chances of some of the diseases if there's less variation. This also happened with the sea otter population. So sea otter population was almost gone extinct, and there was a very small group that was found in Big Sur, and then they basically they rescued that group, and there was a lot of inbreeding. So the alleles that are available for sea otters are very, you know, it's not very diverse gene pool that's available. It's very small. So if a disease, maybe like, you know, we have coronavirus, but another disease comes around, it can wipe their whole population out because there's not a lot of genetic diversity that's left. So that also happened with the sea otter population. Then there is a bottleneck effect. So bottleneck effect is maybe these are your original alleles. This happened with the cheetah population. So these are your original alleles. There's a lot of diversity, and maybe there's an environment that changes, or maybe hunting. Because of hunting, the population is reduced. And then only alleles or very small population is left, or only alleles available are these three. And then you put them in a secure location because you don't want them going extinct, and there's inbreeding that's happening. Now, the only alleles available are these three in this whole population, even if the population is really big now because of inbreeding, but the allele frequencies or alleles that are available are only these ones in the whole population. So only three different alleles remain, and all these alleles are gone. So that's bottleneck. So that can happen due to environment change or hunting or disease. And then there is non-random mating. Mating is rarely random. There is sexual selection. I know Eric mentioned something about peacocks last time, them having, you know, longer tails, but that's also having them hunted down more. I haven't looked into that yet, but that's something that's called sexual selection, mate choice. Um, so mating is rarely random. So there are a lot of factors that can influence mating, including if you know geographical restriction. If there's a physical barrier, you can't go in that place. There is no access to opposite sex. So there are some examples of this. So we talked about, I don't know if you guys, in Hawaii, there is something called stalk eye fly. So what's happening, there's this fly, it has the eyeballs on this stalk here. For some reason, females, they keep choosing the males with the long stalks. So these keep getting longer and longer because these ones are the ones that keep getting picked due to sexual selection. And same thing with the peacocks. Um, their tails keep getting longer and longer because those are the ones that keep getting picked. And there's also, I don't know if have you guys heard about fiddler crab? So so this is a fiddler crab. It has a huge claw. It has no benefit, no benefit of having this claw. Maybe you can just wave it. But females, for some reason, they keep picking the crabs that has this fiddler claw. So they are more attracted to the crabs that has this fiddler claw. So that's sexual selection. So females prefer to mate with a crab that has this. It has no benefit for anything. So that's another example. So that's sexual selection. Migration. So you have this rabbit population of light color here. You have a rabbit population of dark color here. And if so there are alleles or gene pool here, there's a gene pool here, but if one of these rabbits comes in this population, that's going to change the allele frequency in this population, in both actually, because it leaves from here, comes in here. So new alleles are added here and alleles are leaving from here basically. So it's going to change the allele frequency. So immigration coming in or emigration with the E leaving. So that's migration. That's end of the chapter.